Hello, everyone. I'm very happy to be here today to talk to you. I am a professor at MIT, so across the river, and computer scientist. I work with doctors and patients to try to bring the most innovative recent advancements to helping patients and doctors. And today we are going to talk about AI and how AI could help with Parkinson's disease. So one of the things that is difficult about neurological diseases, whether you are thinking about Parkinson's, Alzheimer's, or other neurological diseases, is that we really don't have very good ways of measuring the brain. So we can't put just electrodes in the human brain or take a piece and analyze it. Of course, we have neuroimaging and PET scans, but these are not, like, they're expensive and a lot of overhead to find that, go there, and you cannot do them on a regular basis. So the question that we ask, can we actually provide something that helps people in basically diagnosing the disease, tracking its progression both on the motor and the non-motor functions, but it's just very, very simple. It just works like your Wi-Fi. So here's what we have. In my lab at MIT, we developed a device that looks very much like the Wi-Fi box at home. I'm sure all of you guys have Wi-Fi box at home. So imagine if that Wi-Fi box can sit in the background of the home, analyze the wireless signal that bounces off our bodies, and from that uses AI to extract sleep, to extract gait and mobility, to follow our vital signs, and even our brain waves, or what is called EEG signals. That might sound like science fiction, but actually it is feasible. I don't know why this is, but basically what's happening here is this is a device, we call it Emerald, and the reason why it works, it uses AI. Okay, so basically you all know about AI from ChatGPT, and so ChatGPT operates over text, and from that it can generate text or images. So imagine an AI that operates on these electromagnetic waves around us, and from that can extract our physiological signals. And the reason why this works is because when wireless signal, like you all here, are swimming in a sea of wireless signals, you agree with me, like there's Wi-Fi, there's cellular signals around you. When that signal bounces off our human bodies, because our bodies are made of water, the signal bounces and takes with it a lot of our physiological metrics, like the pulsing of my blood, for example, is on the electromagnetic waves around me. Like when I move, these steps are recorded in this invisible, on these invisible fields around me. My breathing is recorded on them. So what the AI is doing is just to analyze them and extract that information from them. I'm going to show you a few video demos of what we can do. So here what you see is my student and walking, and you can see that the AI is able to track his movement quite accurately, without any wearable devices on himself or anything like this, just purely by analyzing how his movement is changing the electromagnetic waves around him. And of course, everything that we do, we publish in like top journal and top machine learning conferences, and everything is peer-reviewed compared to the gold standard, showing that it's highly accurate. So this is movement, but we can also monitor sleep. So when we go to sleep, our brain waves change and we enter different stages: awake, light sleep, deep sleep, and REM. So REM actually is the stage during which we typically dream. And maybe many of you have heard of RBD, REM behavioral disorder, and like that it is connected to Parkinson's. So in fact, I'm going to show you as we speak more that REM has so many connections to Parkinson's, in fact. And deep sleep is the stage of the brain where we have what's called slow wave. The slow wave is like waves that, electrical waves that span the brain and kind of like clean the brain of toxins. So slow waves are actually important in what we call today the glymphatic system, the system that cleans the brain. And impairment in slow waves actually could contribute to neurological diseases such as Alzheimer's and Parkinson's. So understanding sleep at a deep level is important for understanding neurological diseases. So today, if we want very accurate sleep staging, we send someone to a sleep lab. They put electrodes on the head and the body. This is from MGH Sleep Lab. And this is difficult, of course, to sleep like this. You're not going to go to MGH or Brigham for a sleep test on every night. Now, of course, we have like Apple Watch and Oura and stuff like that, and they are good. I mean, I really encourage you to use them. But imagine that actually we don't have to wear any wearables, and we can get an accuracy on sleep staging much, much higher than what we get from the wearable. We can get something that is comparable to this. So here is our device. It transmits very low power wireless signal, analyzes the reflection with AI, and from that it gets something called the sleep hypnogram. So the sleep hypnogram is what you get in the sleep lab. Like, it tells you for every 30 seconds how the brain is moving from awake, light sleep, deep sleep, REM, and again another cycle, and so on. And again, everything that I'm showing you today is compared to the gold standard, and there are a variety of publications that we have if you are interested in taking a look at them. So this person is sitting like you, and what you see on the screen is his inhale exhales. Because, I mean, basically, as we said, these inhale exhales change the wireless signal. We asked him to hold his breath. You see the signal stays at a steady level because he exhaled and he did not inhale. He's not using any wearables or anything like that. It's just like he can live his life and the environment would follow these physiological signals. And again, everything is compared to the gold standard. In the case of breathing, it's an FDA-approved breathing belt. In the case of sleep, it is the Mass General Sleep Lab. So all of it is compared to the gold standard. Now, I'm very excited about our most recent result, which is the ability to extract the EEG of the person. So the EEG are the brainwave, electrical brain waves. Again, I don't want to scare people. This does not mean that we are reading people's brains. We cannot read your thoughts. But basically, we are accessing the EEG during sleep to extract the circuitry, how the circuitry changed during sleep. So here I'm showing you two examples. This is the EEG measured by putting an electrode on someone's brain. This happens to be an Alzheimer patient, 83-year-old. And this is his EEG during sleep. And this is the AI-generated EEG for him. And as you can see, it is quite accurate. Now, if we can get like measurement of how our brain EEG is changing from one night to the next, without touching the person, without asking them to wear electrodes on their head every single night, then we have a way to actually track diseases that happen in the brain. And we can start improving our understanding both of the disease as well as of the therapy that we are giving to people. So this is, of course, this is one example, but we have done this with over 20,000 different individuals, and the errors are about only 7%. I'm going to talk about how it works, but at a very, very high level, okay? So let's take EEG as an example. So you all have seen systems like this, like probably you have heard of Gen AI, generative AI. And you definitely, if you use ChatGPT, you are using one such generative AI system. So today with generative AI, you can have a prompt that is a text, and you can ask it to generate an image, for example, or more text. So here I give a system called DALL-E, a prompt that says a corgi playing a flame-throwing trumpet, and it generated this image. So what is really important about generative AI is that what is generated and the prompt, they have to be consistent. Okay, so if it generates a cat here, that would not be consistent with the prompt. So now imagine something that looks like this. So instead of the prompt being text, we can have the prompt being the wireless signal that is bouncing off someone during their sleep. And what we are saying to the generative AI here, generate for me the EEG signal, the thing that I would otherwise collect using something like this, generate that for me, but it has to be consistent with this wireless signal, because this wireless signal is bouncing off a specific person at a specific time during their sleep. So it has to be the EEG of this person at that particular point in time. Now, this is, as I said, I mean, it's very exciting for us because like we start being able to understand the brain and measure it in an easy, very simple way that is accessible for everyone. And the reason, again, I just want to tell you a bit more just to give you a very high level appreciation of why actually EEG signal, for example, or physiological signals might use the same type of AI that we are using for text. So if you think about text, so again, ChatGPT. So the reason why AI works on text is because text has a sequence of words from a finite dictionary, okay? The English dictionary. It's a finite set of words. Okay, so I tell the AI there are a finite set of words in this language. The other thing is that there are rules that govern how a sentence, how words follow each other in a sentence. It's not random. It's not like you can just throw like one word after the other and that will generate normal text. Now AI, when you give it a humongous amount of text from a finite dictionary, it starts learning the rules that it can generate text and it can understand text. Now I want to ask you a question. So I don't know how to speak Chinese at all. And I don't know even the Chinese dictionary or the characters or anything like that. Do you think I can train an AI system to understand Chinese? Yes, I'm seeing people nodding. Yes, because I can, although I don't understand Chinese, I can actually train an AI system to understand the language that I don't speak, I don't understand. Similarly, if you think about our physiological signals, again, let's take EEG. So our EEG is a sequence of patterns. These patterns are not infinite number of patterns. There are only finite set of patterns that the brain can generate. And it sounds like words in a dictionary. Okay? We don't know the dictionary, but the analogy works. The same way as I don't know the Chinese dictionary. I don't know what kind of words or characters it has. But similarly, I don't know at the starting point, the EEG dictionary. Also, the patterns, these patterns, the brain generates a sequence of patterns according to certain rules. It's not random. So it sounds like a language that we don't understand ourselves. Maybe like Ray, who's like a neurological expert, understands it much better than me. But I mean, in general, even the best doctors, we don't really know everything about these physiological signals. But probably AI can actually learn those languages, even if the people who are teaching it don't know it. And that's exactly what we use. So we go through 2 steps. In the first step, we call it tokenization, which is let's learn the dictionary of patterns. Okay, so that we call in the lingo of machine learning tokenization. In the second step, it's a generation. It's what generates those patterns, or similarly to like ChatGPT generate the text for you. So it is the generation. But now the generation is much easier because it's generating from a dictionary of things as opposed to like the whole space of possibility. Okay, this is very, very high level. I hope that I convey to you why this could be potentially possible and we can start cracking it. So once we have the ability to start collecting data, humongous amount of data about a brain and changes of EEG and all of that stuff, now we can start asking even deeper questions. I have all of this data about EEG and respiration and all of that stuff. Now I want you to try an AI system that detects Parkinson's disease from these wireless signals that are in the environment. And in fact, so we have used our, we go from wireless signal to breathing to EEG, and then we ask on the generated EEG, does this person have Parkinson? Again, this y-axis, you see this AUROC, just consider it as accuracy. So this is a term metric that we use for evaluating accuracy in AI system. So you can see with almost 90% accuracy, we can tell from one night of sleep whether someone has Parkinson's or not. And this has appeared in Nature Medicine, and now we are extending this to answer other questions, like does this person have Alzheimer's, for example? And we still don't have the same accuracy as Parkinson, but you can see it's pretty accurate, it's around 80%. And we are asking even questions about drugs. We can ask, does this person take antidepressants, for example? And again, you can see it's very highly accurate. So with AI, actually, you hear a lot about AI and what it's doing in the realm of text and images, but also it is changing medicine. And we hope that it will continue to improve our ability, particularly in neurological diseases, where the current tools are not very good yet. So I want to talk a bit about some of the results in Parkinson very quickly. So I told you that we can detect Parkinson from wireless signal. So we did an initial study in this. We asked the question, can AI detect Parkinson from nocturnal breathing? So this is really interesting because so we all, typically we detect Parkinson's disease from motor symptoms, like from the tremor, the rigidity of the movement, because this is what, first we notice. But one of the things that we know also is that by the time the motor symptom appears, the disease has started a while ago in the brain. Okay, so we know in these neurological diseases they start much earlier, and in fact, I mean, we don't even know if we can detect them much earlier. Probably it is much more possible to avoid them. If you can detect a tendency toward Parkinson, for example, very early on, maybe with exercises, with change of lifestyle, nutrition, we can try to delay the disease, change the trajectory. We don't yet know. But the one thing that we know is that we want to detect Parkinson from things that happen earlier, which are what we call the autonomic changes. Changes to respiration, changes to sleep, changes to the GI system, these things tend to happen earlier. So in our case, we ask, can we detect Parkinson just from the breathing of somebody when they are asleep? So we took these respiratory signal. We have the ability to extract them from the wireless signal. We trained the neural network to answer two questions. Does this person have Parkinson's disease? And if yes, what is the severity of their disease according to the MDS-UPDRS, which is the gold standard for assessing Parkinson's? And this is actually a very large study. Basically, my collaborator is the next speaker, Dr. Ray Dorsey, who you're going to hear from him just after me. And also, we worked with MGH, with Mayo Clinic, with a variety of medical centers. And we have more than 7,000 different individuals, 700 of them have Parkinson's disease. And let me show you the results. So, I mean, many of you probably have not seen these styles of graphs before, but this is something we call the rock graph. On one axis, we have specificity. On the other axis, we have sensitivity. But the only thing that matters is this number, the AUC, 90%. 0.9 is 90%. So with 90% accuracy, we can detect Parkinson's disease from the wireless signal that bounces off someone during their sleep. But also we can detect it from breathing if it comes from breathing belt, because I mean we don't care whether the wireless signal is much easier to get a breathing signal from wireless because you don't have to wear any like sensors on the body. But if we put a breathing belt on someone, we can also have the AI from that detect that whether they have Parkinson's or not. So again, like these are like early results, although we have 7,000 individuals, it's still like in medicine, you need multiple results and we need to investigate further. But at least we can tell from this an initial screening of like whether someone has Parkinson or not. And hopefully we can do it before the motor symptoms appear because we are not relying at all on the motor symptoms. And then one could like recommend additional tests like PET scan and stuff like that. Now, of course, if we have the ability to detect Parkinson's from respiratory signal, from things that have nothing to do with motor symptoms, now natural question to ask, can we detect it before actually is diagnosed by a doctor? And here are our results. And again, let me explain this. So this is like to say that we can detect Parkinson before it's diagnosed, it's really hard because I cannot sitting here know who's going to be diagnosed, I don't know, 5 years down the line or 10 years down the line. But it happens that there was a data set that we were able to access, which has breathing signal from 2 visits to a sleep lab. And those breathing signal and those 2 visits are separated by 6 years. So in the first time, there are people, about 500 individuals came, and they measured their breathing during nighttime. And then 6 years later, they came again, but 12 of them, when they came again, said, I was diagnosed with Parkinson. We don't know when exactly, but sometime along this axis between the first visit and 6 years later. And here what you see is these are the people who did not have Parkinson in this first visit and did not have Parkinson's also in the second visit. And these are the people who, in the first visit, they came, they didn't have any diagnosis of Parkinson, the blue ones. But 6 years later, when they came back, they said, I was diagnosed with Parkinson's. So what is really interesting is that the AI already can tell that there is a difference. It's like, because this yellow line, the 0.5 is the threshold between Parkinson and no Parkinson. And you can see that for 75% of those people, it's saying, no, I think I can see some traces of what I consider Parkinson, what I was trained to consider to be Parkinson's disease. So what this tells us is that AI can have the ability, even much earlier, prior to diagnosis, to see traits that are associated with the disease that are not visible, because actually we are talking here about breathing. We are not even talking about any motor symptom, breathing during sleep. So, of course, again, this is even a smaller data set. It's only 500 individuals. So we have to do a lot of work to establish this at much bigger scale, understand exactly how early we can detect. What are the differences? Are we detecting just Parkinson or all like a variety of different neurological diseases? We have to do more work. But the thing that I want to convey to you is that with AI today, we have new power that allows us, without putting electrodes in the brain, without have people live normal life, but be able to see what is going on, how things are developing in one's brain that could have implication downstream. And with that, hopefully, we can start treating early, we start having better understanding so that we can attend to the disease and the patient, as well as having new drugs and therapies. So the other thing is that we have the ability to detect the progression of the disease, because I'm sure many of you know, like when someone with Parkinson goes to have an MDS UPDRS test or something, they have the talk test. They ask the person to walk. They measure how much time it takes for them to walk. What is their speed? Is the speed changing? I mean, that is something that we should be able to measure all the time in the person's own home from their movement. We shouldn't wait for 1 or 2 measurements that we do in the office of the doctor. On a bad day or a good day, that may not be representative. So what we do here is that I told you that we can actually, let me show you this. I told you that we can measure gait and gait speed from the wireless signal. So what we did here, we monitored individual in their home for 1 year. So I'm going to show you just an example first, and then I'm going to show you the cohort. So these are 2 people. This is a person who has Parkinson's disease. This is an age-matched control individual who doesn't have Parkinson's disease. And this is time in months. So this is about 1 year, and here also 1 year. So what we have on the y-axis is the gait speed at home. So you can see that both individuals, I mean, they are slowing down. I mean, these are both people in their 80s. So they are slowing down. Even the person who doesn't have Parkinson, there is a minor slowdown over that 1 year period. But you can see that the person who has Parkinson is slowing down much faster. So now these are 2 individuals, so you might be something just special to these people. So again, we do some mathematical statistical analysis based on something called linear mixed effect model. And these are the combination, what we call a cohort, the result of the cohort for people who have Parkinson and people who don't, who are age matched. And you can see that this is not special to these 2 individuals. In fact, when you look collectively at people who have Parkinson's and people who don't but have the same age, you will see that people who have Parkinson's, they're going to slow down faster than the people who don't. So that gives us also a way to assess the progression of the disease in the motor symptoms. And the reason why this is very important is that as we try to develop drugs for Parkinson's disease, one of the difficult things in Parkinson is measuring that, okay, I developed a drug, it's good or bad. It's really hard because I have to wait for a very long time to see whether the motor symptoms have changed. So here we put on the x-axis, this is a hypothetical drug. Let's say that somebody developed this drug, and the drug may have an effect size, a treatment effect size of 100%, so it cures everyone, or it might have a treatment effect size of 30%. So it cures 30% of the people or 30% of the symptoms. Now, if we want to test that drug to see, okay, so is it really effective, we have to wait for the gait to slow down for some time. And if you are trying to measure gait using the MDS UPDRS, which is what is used today, you're going to need very large number of people. In comparison, if you are using this metric of a Wi-Fi box in people's home that is capturing every time they move, you have so many measurements, so you can actually very quickly with a smaller number of people decide that this drug is effective or what is the efficacy, the effect size of that drug. So it's also very important for routine care. So when we have Parkinson, I mean, nowadays levodopa basically is the drug that we have for Parkinson's. And levodopa, unfortunately, does not cure the drug. It just manages the symptoms. So what I'm showing you here is the response to medications. This is one example. On the x-axis, you see time. So 4 means 4 a.m. in the morning, 5 a.m., 6 a.m. And on the y-axis, you see the movement, the gait speed, the walking speed of this individual. And this is something we call box graph. It is averaging 2 months of information. So when you see he's walking at 5 a.m. in the morning, it doesn't mean that he always walks at 5 a.m., but there was some night during which he walked at 5 a.m. in the morning. So just focus on this red line. So this person takes their levodopa around 6:30 a.m. in the morning, and you can see how, like the gait speed, their ability to walk and their agility immediately goes up. Now, within about 2 hours, it starts going down again. The effect of the drug starts wearing off. So again, the gait, the walking speed goes down. Now they take another levodopa pill here, and then again it goes up, and then every time they take a levodopa tab, it just goes up again. Now, this is actually problematic. You really don't want this movement fluctuation during the day. We call that on-off behavior. You don't want this like up and down throughout the day. So what we want to be able to control these things through the drugs to just make this line flat. So how can we do this? Actually, let me just go here. So here is another example. This person has only 3 peaks, and this is the time when he takes the medication. So you can change the medication schedule, which is exactly what the doctor did. So instead of having 2 tablets 3 times per day, the doctor is just like, okay, so we want to flatten this line. Let's just have 1 tablet 6 times per day. And now you can see that the line is much flatter. There is way less fluctuation in the motor symptoms throughout the day. And it's the nice thing is, like, notice that this is exactly the same amount of levodopa. It's just the schedule is different. Because we understand now what is happening and how the schedule creating this fluctuation in the gait. I want to end with sleep. Sleep is very, very important. The speaker before me was emphasizing that we need sufficient amount of sleep. But I want to talk deeper than that. I want to talk about the type of sleep that we have. So let's look at sleep. I mean, who has seen something that, who knows like about deep sleep, light sleep, REM in the audience? Okay, some people. Okay, so as we said, when we go to sleep, so this is like on the x-axis is time, and on the y-axis is different type of sleep. So you can be awake, you can be in REM sleep, you can be in light sleep, you can be in deep sleep. So this is sleep onset, and then after sleep onset, the person moved to light sleep, and then they moved to deep sleep, and then they moved to REM, rapid eye movements. This is the stage in which we dream, typically. I'm sure you heard that sleep goes in cycles. So every cycle, and typically with REM or with awakening. So this person has 4 cycles. 1 cycle, 2nd cycle, 3rd cycle. The last cycle, they woke up. Okay? This is someone who doesn't have Parkinson's. Now, you guys probably have heard of RBD, but REM sleep is very, very important. It's important for the emotional wellness of the person. It's important for regulating respiratory signal and cardiovascular signal. It's actually important for our mood. It's important for variety of things that are what we call autonomic things. So, and I'm going to try to track how REM changes between someone who has Parkinson's versus someone who doesn't have Parkinson's. So let's try to look at that. So here what you see, first, control means they don't have Parkinson. Prodromal means they have early, very early, they like hardly have any diagnosis yet. And PD means that people have Parkinson, diagnosed Parkinson. You can see that as a person moves between like not having Parkinson to prodromal to actually have Parkinson, we have less REM sleep. But it's actually much more complex than that. So again, let's go back and remember REM is cyclic. Every sleep cycle typically ends either in REM or in waking up. So what happens if I try to look at these REM cycles and night after night after night after night? We have, like, from wireless signal, we can get sleep every night. I mean, in someone's home, it's very easy. They don't have to do anything. So let me show you that. First, I'm going to show you in someone who's controlled. They don't have Parkinson's. So in the x-axis, you see 0 means sleep onset, and this is the sleep time. So this is 3 hours after sleep onset. This is night after night after night. And black means no REM. Any color other than black means the person their brain is in REM. So very clearly, you all see the cyclic behavior of REM. Every sleep cycle ends in REM, or it ends in awakening, particularly the last sleep cycle typically has tendency, we wake up in the last sleep cycle. Let me show you, so these are REM. So let me show you someone with Parkinson's. So what happened is, now it is more pixelated because we have fewer nights here, but that's not important. What is important is that we have less REM, and not just less REM, this very cyclic structure got impaired. And that actually is very important. It's indicative of a variety of other things that are not just sleep, like, for example, effect on mood and other autonomic functions that the person might be having. And in fact, this effect of losing the cyclic architecture of REM happens over time. So here I'm showing you 4 Parkinson patients. This one is, I think, about, as I remember, 3 years after diagnosis. This one is 5 years after diagnosis. This one is 19 years after diagnosis. So with time, as the disease progresses, it's really like eating up this REM architecture that we don't even see. I mean, this is happening during our sleep. And here's just control people, just so that you can see the difference. So, I mean, we see the motor functions because they are very obvious. I mean, that's something that we see on a daily basis. But really, there is something that is even equally important that is happening during sleep that is affecting the brain and manifests itself in a variety of autonomic changes and dysfunctions. So understanding that is very important, and being able to monitor and start having that understanding so that we can, like when we have drugs and treatments, we can not only look at whether the motor symptom improved, we can also look at whether this structure is pushing back, whether the treatment is pushing us to this as opposed to here. I want to show also, so you see that this is how regular the REM, and this is like over years, and this is just similar to the previous graph here. So this is over time, the REM cyclic architecture get impaired, and this is like 25 individuals, and you can see again over time that cyclic structures get impaired. Now, I want to leave you with one nice thing. So we are working with doctors in a variety of clinical trials, and some of these trials we are starting to see a treatment that we are seeing them recovering that nice REM architecture, at least partially. So we see things, hope that we're just like, okay, maybe this is going in the right direction. So I will end with this, and basically, I hope that in the future we will have much better ability to understand diseases, neurological diseases such as Parkinson using AI, be able to both understand them and treat them in a better way and attend to the patients and help the doctors help you. Thank you.